Hi people, my name is Victor. I'm going to give the introduction about this lab. Is calling the number 6. In this introduction, we're going to explain what's going on and what we do with this lab. In this experiment, we explore how the current carrying wire behaves and plays inside the magnetic field. When the electric current flows through the conductor, experiences a magnetic force pull. Magnitude depends on four key factors: the current flowing through the wire, the length of the wire within the magnetic field, the strength of the magnetic field, and the angle between the wire and the field. This relationship is described by the equation. In your setup, the angle between the current and the magnetic field is fixed at 90 degrees, which simplifies the equation since C 90 degrees equals 1. This allows us directly to relate force, current, length, and the magnetic field strength. The goal of this experiment is to determine the magnitude of the magnetic field produced by the magnet. When we do this, measuring how the force acting on the system charge, as we vary the current flowing through the wire loop. By collecting data and analyzing the linear relationship between the force and the current, we can calculate the magnetic field strength. To verify your results, we designed the second experiment using different circuits. We use calculated magnetic field value to predict the force, then compare it to measuring values, allowing us to evaluate the accuracy of your experiment through the expression error. Through this investigation, we gained a deeper understanding and the interaction between the electricity and the magnetism, and whether as well the relativity with experimentation in physics. Thank you for watching.
Materials. For Lab 7, we are investigating the magnetic force on a current-carrying wire placed inside a magnetic field. The purpose of this lab is to determine the magnetic field strength of the magnet by measuring how the force changes as the current changes. For this experiment, the materials we need are a main unit, a current loop, a magnet assembly, a lab stand with a rod that is 3/8 inch or smaller, a weight balance with at least 1 gram sensitivity, and a power supply. We also need a way to measure the length of the current loop, since the wire length is one of the variables in the magnetic force equation. To set up the experiment, first mount the main unit securely onto the lab stand. After that, choose one current loop, measure its length carefully, and plug it into the ends of the arms of the main unit, making sure that the foil extends downward. Next, place the magnetic assembly on the weight balance, then move the stand into a position so that the horizontal section of the conductive foil passes directly through the pole region of the magnets. One very important thing is that the wire must pass through the magnetic field region, but it must not touch the magnets. After that, connect the power supply to the main unit. Before beginning, double check that everything is aligned correctly, the loop is secure, the magnet assembly is centered on the balance, and the balance is stable enough to detect small changes in mass. Once everything is in place, the apparatus is ready. The setup allows us to absorb the changes and current effects, the magnetic force, which will help us calculate the magnetic field strength. Procedure. For the procedure of Lab 7, we begin by measuring the mass of the magnet holder and magnets while no current is flowing. This gives us our baseline measurement. Next, set the current to 5 amps, which is the lab is treated as negative 5 amps based on the chosen direction of the current. Once the current is applied, measure the new apparent mass of the magnet assembly and record it in Table 1. After that, descend the current by 1 amp at a time. At each step, measure the new mass shown on the balance and record it. Continue doing this until the current reaches 0 amps. Once you've reached the 0, reverse the direction of the current by switching the power supply cables. Then begin increasing the current again, 1 amp at a time, measuring and recording the mass each time for the positive current values. After collecting all the mass data, convert each mass value into force by multiplying by 9.81 meters per second squared. That gives us the force values needed for analysis. In the data analysis portion, enter the current and force data into Capstone using manual entry. Rename the axis columns with the current experimental names and units, then fill the table from table 1. The graph should update automatically. Because force and current have a linear relationship in this lab, apply a linear curve fit to the graph. Use the equation from the graph to solve for B, the magnetic field strength. Finally, for percent error, select another circuit, measure its wire length, and use your calculated magnetic field to predict the theoretical magnetic force at a current you choose. Then perform the experiment, measure the actual magnetic force, compare the two values, and calculate percent error. This let us know the accuracy of our investigation.
Hello, my name is Jorge Saniceros, and I'm going to be going over Lab 7, Data and Data Analysis. So for this lab, we have a standard length, which is 0.0064 meters. And we have to put, for our first table, we have to set different currents and then decide how much mass the object is applying to the scale. So then first for -5 current, we saw it was 0.1574 kilograms. And the force acting upon it was -0.014715 newtons. For -4 amps, it's 0.158 kilograms. -0.008829 newtons. For -3 amps, it's 0.1582 kilograms, with a force of -0.006867 newtons. For -2 amps, it's 0.1584 kilograms and a force of -0.004905 newtons. For the current and -1 amps, we have a mass of 0.1588 kilograms and a force of -0.00981 newtons. And now for current and 0, which is our base, we got a starting mass of 0.1589 kilograms and a force of 0. For 1 amp, we have 0.1592 kilograms and a force of 0.002943 newtons. For 2 amps, we have a 0.1595 kilograms with a force of 0.0058886 newtons. For 3 amps, we have a mass of 0.1598 kilograms with a force of 0.008829 newtons. For 4 amps, we have 0.1601 kilograms with a force of 0.0012 newtons. And for current, for 5 amps, we have a mass of 0.1605 kilograms. For force for that one, we have 0.01569 newtons. So for table 2, we have the linear relationship between force and current. And for this table, we just had to determine what the different values mean in our current equation. So we have the original equation, which is y equals mx plus b, which is standard. And our equation, which is fm equals lbi plus f naught. So then we see that y is equal to fm, m is equal to lb, x is equal to I, and b is equal to f naught. And for our third table, we have calculating the magnetic field. We see that m is just lb over I, so that's how we get 0.00241. The L is 0.1064 meters, and the B is 0.3765 T. And now for our table 4 percenter, we have a length of 0.013 meters, a B of 0.001 T, a current of 4 amps, and then the theoretical Fm is 5.2 times 10 to the -5 newtons, and our experimental Fm is 0.0039 newtons, so then that gives us a percent error of 7.4%.
Okay guys, this is the conclusion already. In this experiment, we successfully determined the magnitude of the magnetic field by analyzing how the magnetic force current carrying while the charge with the widening current. The result shows a linear relationship between the force and the current, which is consistent with the equation of ILMC. Since when the angle is fixed 90 degrees, using the slope of your graph, we are able to calculate the magnetic field strength. Then we use this value to predict the force of the second setup. When comparing your predictor and measurement values, the percent error provided insight into the accuracy of your experiment. Possible sources of error include measurements, uncertainties, slight misalignments of the wire with the magnetic source of error. Include the measurements, understanding, slight, and the field fluctuation in the current overall. The experiments demonstrate the direct relationship between the electricity and the magnetism, and show how the experimental data can be used to determine physical quantities with the relational occurrence. Thank you for watching.
For materials and procedure, Pablo. For video editing, recoding and conclusion, Manuel. For intro and conclusion, Victor. Thank you for watching this week's lab report.